Hello everyone, welcome back to Dragonfly Engineering. So this week we got another quick machine part that we're going to do, and this one is going to be a connector for electrical armored conduit. So armored conduit is basically sheet metal that's stripped and then bent in a kind of a continual cup and sleeve style, and then it's spiraled on itself. So it crimps on to its previous spiral, and it creates this flexible metal conduit that you then run electrical wires down the middle. So if you look above most drop ceilings and the lighting fixtures, will typically have this armored steel conduit that connects to the lighting fixtures themselves. And the way to connect this steel conduit, the NEC standard steel conduit, is that you create a spiraled nipple basically, and this thread that is on this hollow tube that connects to your junction box actually threads onto the inside spiral that's created by this armored this armored jacket. It basically thread locks in, and in the middle of this tube, the wires that are passed through the armored spiral metal jacket pass through the tube into your junction box. Our task today is to actually make this mounting interface with these hollow tube and the spiral thread that will screw into this armored electrical jacket for basically anchoring the armored conduit onto a box. So that's what we're going to make. So let's open up and I've already modeled this in SolidWorks, and I've actually machined a couple of previous revisions of this part, but I had to make a new base flange for this particular one. So let's start off with starting the recording on the computer screen here. So I'm going to bring up Mastercam, and we already have our part loaded. Now so here we're seeing all of the toolpaths for this part, and so we can hide the toolpaths by hitting Alt-T on the keyboard. So this is our part that we're going to make. This pink plane I added just for machining purposes, but yeah, that conduit will thread onto the outside of this tube, and this special thread here we're going to machine into the tube itself. And when you screw this conduit on, it basically locks in, almost like a finger trap type of interlock, because it all kind of strains up in there. And then we've got a couple of, I believe these are threaded M3 holes, and a flange for our part. Now, as I mentioned, I had a previous revision of this part, and I've already machined all of this on the previous revision. But I had to change and add an extra wide flange with this step. So you can actually see the original part is underlaid on our new part. And if we go over to levels, you can see that I can turn visibility on and off for the two parts. So if actually let me turn on, okay, so this is our original part. Well, actually you can check out just the plane and the wireframe too. So I added this pink plane, but let's turn on the original part again. And I actually did all the toolpaths under the toolpath section. If we click on the bottom and this plane over here, all of these toolpaths originally were for this original part. There we go. But you can see that now the toolpaths are kind of mimicking the new part, because we're machining way out here even though the part's over here. So what a nice trick with Mastercam is if you have a new part that's similar to your old part, you can actually merge in a new part under File and then Merge, and you can pick your part and your new part and stick it in there. But in our case, I've already done that. And you basically just drag your new part over the existing part. In our case, all of the structure of the helix didn't change. I just changed the base flange. So if we go back to levels and we turn back on the new part, and actually we can shut off the old part. So you can see how the old part kind of appears and disappears. I should probably change its color. But anyway, we've got both parts interlaid on here. And some of these tool paths, because the structure of the first rev and the second rev didn't change, I actually didn't have to reassociate the tool path to the new part. But by overlaying it, it's going to machine the same thing anyway. But down at the bottom, we did wind up having to reassign some of the operations to the new part. So if we go back to toolpath, the first operation that we're going to do is this dynamic OptiRough. And it's a pretty smart little subroutine that Mastercam does. So basically what it figures out is how to machine away all of the rough material around your finished part here, hogging it out basically, using the full face of the end mill and doing things like, for instance, these brown paths that you can see here are rapid repositioning to take out more bites of the stock without the end mill having to jump all the way up and out of the stock, like you can see with these yellow tool paths, which it's pretty nice, you know, because it optimizes speed of machining. So if we click on parameters, and these are kind of the instructions to tell the toolpath software what to do about the model that you give it. In our case, you know, we selected geometry and we selected basically everything. So I just window selected the whole part. And if you need to avoid areas, like you don't want to machine certain things, then you would click on other features and they would highlight in red. And then Mastercam won't allow the tool to cut into those avoidance regions, is what they call it. Things like toolpath control, you can tell it to machine on the outside if your part is such that you need to basically machine everything like we're doing in this case. Or you can say keep the cutting on the inside if your circumstance is such that you actually have other features outside that you don't want to cut into, then you can say cut on the inside. And then you can always preview your new toolpath options with this blue check. So if we do that, you can see it recalculated, and now it's only just trying to cut the inside, but it's not going out and machining like these side walls or anything like that. But in our case, we want to cut everything. So we're going to click outside, hit the blue check, and now it's decided, oh yeah, we're going to cut everything again. Tool is a 3/8 flat end mill, and you can define the holder and everything like that, as well as the extension of your end mill so that you don't wind up plowing your tool holder through your stock, which I think everyone has done at least once in machining, at least CNC machining, and a whole bunch of other little things like planes, for instance. This operation is all from the top side, but other operations are going to be cutting from the side since this is a 5-axis milling machine that we're going to use, the Haas UMC 750. Probing options. Oops. This isn't a touch screen. So we're going to do a G54 work offset. We jog the position that we want. Probe Z, yes, we want to probe the Z axis, or yeah. And then the Z surface is minus 0.5 inches below approximately where we set our probe. And then the X dimension is approximately 6.25. Y is 1. And we want to probe Yeah, half an inch below the Z surface is fine. All right, now I'll hit cycle start. And it should probe the block. It does like a coarse touch and then a refined touch. Okay, now we are at the exact center of the block, but our part is going to be offset to the left, so I'm going to manually offset to the left once I check out the CAD system and see how wide our part is. And we can also show a preview with the back plot option, so we can show how it's going to machine like that. And I'm just dragging the play slider forward and back. But let's see what the actual toolpath looks like on the Haas. All right, I'm out here at the Haas UMC 750. Got our camera ready to watch the machining. And we got our program loaded over here. It should be exactly the same as what was on the computer. And I've got the feeds and speeds slowed down because I'm going to try to run this without coolant. But this is the Haas control. And we are going to hit cycle start, and I'm immediately going to put my finger on the feed hole just to stop things if things don't look right. And be ready to stop if we need to. First tool is a 3/8 end mill. Now we are going to have a deep cut here. That's a hefty cut. Normally this would be going twice as fast, but you need coolant when you go super fast with aluminum, otherwise it'll weld onto your cutting tool and break it off. Or clog up the flutes with molten aluminum or smeared aluminum. Okay, so the next feature we're going to do is flow 5-axis. So here we're actually going to attempt to cut this helical 3D surface that kind of goes all the way around the part. So to do that, we are going to use the 5-axis or multi-axis area of the tool path options, and flow is the one we're using. You can, depending on what you're doing, you pick all these different 5-axis machining operations. So, but we wound up with flow. So if we take a look at the parameters in flow, even though this is a 5-axis, we've locked the tool axis control to this top plane. So it's gonna, basically the keyway cutter is gonna be locked into a 3-axis operation. So it's really a 3-axis thread cutting, a fancy surface profile thread cutting that we're doing here. And see, cut parameters up here, we can show the surfaces that we selected. So we're basically going to profile cut with a three-dimensional raster cut, basically, which is all of these blue lines out here. This is the center of the key set cutter that we're using with a radius tip. And if we want to see what that looks like, oh, I gotta end the selection first, and then answer a couple of questions about, you know, like tool direction and all that. But we can get out of this because we're happy with it. And we can show this toolpath with the back plot here. So we'll drag, and you can see our key set cutter has a full radius tip. And there are some issues with this cut. As you can probably see, you know, this helix is actually more complicated than what is represented with just a flat cutting tool that isn't actually changing its orientation to cut underneath this profile. So we actually do wind up cutting away some of our rounded tip here, and you can see that with the kind of the first preview that we're going to show that Mastercam does, basically just animating the travel of the tool. But as we go back and forth, so it's going to climb all the way up and then all the way back down, and it's going to follow this profile until it completely profiles the entire part. But you can see, again, as this flat disc is traversing a three-dimensional helix, it's cutting off the tops and bottoms of our profile here. It's a little hard to see right here, but if we get perpendicular, you can see how it's actually cutting in. And in fact, I actually wound up with a little bit of an undercut for this cutter. I actually have it cutting deeper into the surface than what is modeled here. But anyway, there is some issue with this toolpath in that it's, for one, it's not a full 5-axis in that this tool is actively clocking itself as it spirals around. But for simplicity and for this part, I just kept this tool locked at vertical instead of full 5-axis kind of rotation as it's cutting the spiral. One, because I'm not good enough at Mastercam to make that happen at the moment. But two, I kind of like the sharp tip that it's going to create. So let's take a look at this cutting operation on the Haas mill. We can go at full speed on this. It's doing a zigzag cut. That's why it's changing directions. It's going all the way to the top, looping out, looping back in, and going back down. All right, now we're back. So you probably saw how there was basically a big scallop on the walls of this part from cutting this helix. And to fix that, I wound up with using a flat keyway cutter instead to basically clean up these walls. So if we look at the tool, our next tool is basically the same key set cutter, except it's got a flat tip instead of a full ball, a full round radius tip. And this tool actually is going to clean up this simple cylinder between the threads that were the positive threads that we're machined with the previous flow 3-axis or 5-axis milling operation. That way we don't have to worry about having tons of overlaps to clean up and make tiny little scallops. We're just basically just using a flat-faced keyway cutter. So we can show that profile as well. And actually an interesting thing with this one is that the original toolpath is actually ghosted. So this path that you're seeing will not actually go out to the mill. But I used this first toolpath to create transforms because we got to clean up this entire face between this dotted line and that dotted line. So I basically started with a helix, probably following this line and offset below it. And then I wound up doing an array and transform to basically offset that first cut and make multiple passes. And I did that on the upside and the downside. So now you can see the width of all these copies of that first helix cut basically matches the width of our flat cylindrical plane between the positive helix. And so yeah, let's see how this cut looks on the mill. Now we got the square-ended key set cutter or keyway cutter, and that's going to clean up the interposed surface and all these tools are set off the tool setter, so I didn't really have to set up anything other than put the stock in this mill, because the mill knows where all the tools are located as far as their height from the mill zero. Okay, so we're back. Now that those helixes that we cut didn't actually get all the way to the bottom, so you can see this transform here down where the red portion of the toolpath. This is basically the lead out. I had it lead out following the same helix. It doesn't come and clean up the bottom transition from the cylinder to the base of our part. So I threw in a couple of simple contours like this to clean up the bottom. And then there was another contour that I added, which I actually had to draw in a geometry right here. That's this line. And you can see that light blue contour line to machine off the end of our helix, because the other tool paths kind of just created this infinitely sharp lead out in the metal. But I wanted to blunt this off because it's easier to screw into the electrical conduit, or the flex conduit. So let's see how this back plot looks. So if we drag our playback slider, you can see how I'm engaging the front of our thread here with our cutter, and this path is the contour that we're going to follow. So it shouldn't actually cut into the cylinder. We are cutting off a little bit of the tip of our thread, but it doesn't really matter too much because it fully functions as machined. So yeah, that was the final little cleanup that we did right there and then pulled out. And then the rest is a bunch of drilling operations. Oh, let me get out of that. And we drill out the middle, and then we contour the inside bore with a 1/4" end mill, and then come back and do finish cuts from the OptiRough, the original OptiRough. Cut a lot of that away, but it leaves stock behind so that you can go back and do a finish. So that's what all of these are, kind of just final finish cuts. And then drilling and tapping our mounting holes. And then the last operation is to part off the part from the stock. So this is really the only 5-axis operation, because if you look at the parameters for this cut under planes, you can see our work coordinate system is still top, but the tool plane and the construction plane are now front, which if you click on the little orientation box in the bottom left, you see that we'll reorient to the front. So in reality, for this cut and the other cut, the mill will actually rotate the part to the side like this, and then we'll machine off the part this way, and then it'll rotate the part 180 degrees. And then for the final cut, which is the second contour, operation number 17, you'll see under planes that we're now cutting on the back plane, where the coordinate system, the work coordinate system is still top, but now we switch to the back. So that effectively rotates this part 180. And then we machine off the back. And we can back plot that as well. Excuse me. Like so. So you see how the end mill is going to come in and cut off the inside until there's basically just a little tab of metal left, and then we just break the part off. What we can do now is to really see what our shape looks like with that key set cutter parallax problem that I was talking about. And to do that, and also just to confirm, that you're not going to crash or have any major problems with your machining operations that you define, you can select everything on your toolpath tree. And here's all your toolpaths kind of muddled, but it's difficult to really see what's happening in here. But we can do a verify selected operations with a true mass removal simulation of machining the part. So we'll click that, and then this window, or this kind of associated application, opens up, and we can drag it open. And you'll see that it actually follows the orientation, of our workspace in Mastercam. You'll see that this thing is kind of following along. So normally I have this window and a second monitor, but for now we can just run it as is. So what we're going to do is simulate the machining of our block of stock, which was defined in Mastercam. It's just not shown right now. So let's hit play and see what happens. Yeah, we're at pretty good speeds. So this first cut is the OptiRough cut, which was describing as a pretty smart algorithm in Mastercam. I guess we can bring this to full screen. Let me pause it. Since I'm recording the screen, it's a little sluggish and dragging. Okay, let's play now. And it'll show you how the parts are machined. Now here is our full round key set cutter that's cutting our thread into our shaft here. And it's looking to see if there's little problems like gouges, and it's showing you the actual shape that we're going to get. So you can kind of see it's a lot sharper out here than one would expect from the actual 3D model that we did. And then the rest of the operations cut so fast that we didn't even see it. So, but another thing we can do is actually color code each cutting operation under color loops. So here you can see each machining operation has its own color. And down here in the kind of the progress bar, you can see the different colors for the various different operations. And all of the quick stuff just happens here at the end. Let me optimize this screen. Here we go. Now we can reverse and see exactly what's going on. For instance, we see a little gouge right here. The red means gouge. And again, every machining operation has its own color here, which is kind of cool. So we can go all the way back to, in fact, we can just reset and just play this again with the color coding. So the first cut is yellow. Oh, I think I need to, let's rewind again. I guess I need to hit this color map. There we go. Okay, let's see what happens. Oh, now they're like pastel colors. Interesting. So the first cut is yellow. This is the Opti Rough, which takes away most of the material. Oh, okay, and then we're getting, the next cut is the blue cut, which is the 5-axis flow cut. And you can see the Opti Rough actually roughed away some of the flow cut as well. You know, kind of there's some tool blend there. And then just some of the tips of the, well, it was there, but now it's gone. Oh, and then it really blasted through the rest. So we can still back up. I think we can actually zoom in on the toolpath. Well, we can drag this and slowly go back. So here's where center drilling, and then drilling for our tapped holes, and then we actually tap the hole itself. And then we change orientation, and then we machine off the bottom. And again, you can see each color is its own operation. So that's what we got. I wonder if I can fix orientations. Or maybe I can do that in Mastercam as well. So I can go back to the machining window and I can click on front here. And then I can switch back, and then the simulation follows that color, or follows what you're doing on the main Mastercam screen. So yeah, there we go. Anyway, so you can see how the different colors cleaned up our face with that square tipped key set cutter. And then we still have kind of a weird sharp edge, but that actually works out well with the conduit. All right, so when we're happy with the results of our simulation, which I am, then we can go back to the Mastercam window and we can click on Machine Group, or click on particular machining operations that you want to send to the mill. You don't have to actually send all of the operations. Oh, and this little red arrow is like where your next milling operation is going to go, so you can reorder your milling operations. But in our case, we're going to post everything, so I'm going to click Machine Group 1, and then this G1, Post Selected Operation. Ask what the file name is. I am going to stick this USB stick in the computer, and the post processor just created this G code, which the 5-axis Haas UMC 750SS can read. Postability is the company that makes the algorithm that creates all of the G code, and this is all the information for the mill. Just a whole lot of lines of code to machine our part. And Mastercam, I think it defaults to making millions of little line segments, but you can also have it post out arcs, you know, to save on just, you can have it tell the mill to just cut a circle instead of cut a little line, a little line, and a little line that all adds up basically to the same circle. So it seems like it defaults to millions of little lines, but in this world, I guess it's not a big deal, but you can get a disco ball effect. So you can either do line smoothing, or you have to tell it to post out actual arc commands, a G command for arc instead of linear line segments. Okay, and then so we're set. So this file exists on the E drive, which is that USB stick. So let's run it and see what happens. right, now we're going to face off the part. And there we are, finished part. I'll open up the door here. Okay, here's that flex conduit I was talking about. It's just a spiral of metal. This is the other end that's kind of been cut. But yeah, you can just see how it just continually spiraled, and this is in a lot of houses and industrial buildings for electrical service. But it looks like that on the outside. So let's see how we, well, actually first let's check the fit. Feels good. And then we spiral this on. And it's anchored. And then we can break our part off. Like so. Now I do need to face the bottom. This isn't a true like one-op part, even though it's on a 5-axis. So I gotta clean up the bottom and then drill and then counter bore or countersink to edge break for the wires, so the wires don't get cut on sharp metal edges. But anyway, that is our part. So thanks for watching Dragonfly Engineering, and I'll see you guys soon.